Okay, so welcome everyone to today's meetup. This is the first event of the year for Connected Data London, and we're happy to welcome our first speaker, Aleksa Gordic from Microsoft and AI Epiphany, who will be talking about his journey in the magic world of graph machine learning.
Awesome. Thank you, George. So first of all, over the last year and like 3-4 months, I've been intensively going through different subfields of machine learning. And one of those was GraphML. And the reason I'm talking about GraphML today is because it's so exciting. There is a lot of hype in the community. You're probably already aware about it. Like just looking at the metrics, like the number of published papers in GraphML this year is even higher, I think, than GANs. I may be wrong on this one, but there is a lot of hype, and it's not without a reason. Basically, there is a lot of exciting applications happening in GraphML currently. So today I'll try to kind of convey my experience with this area, and I had the luck to collaborate and communicate with the best researchers from this field. So by no means I'm an expert in this field, in the sense that certain people devote all of their time doing just GraphML, so they spend like 4 or 5+ years doing it. I'm still a novice. I did do and learn a lot. I open sourced, maybe you even saw the Graph Attention Network project from scratch. So I did learn a lot, but I'm still not as an expert as some people are. So just a disclaimer. Without that further, let's just continue. And because this is GraphML, let's start with graphs. So basically, GraphML deals with graph type of data, and you probably already know this, but let me just recap. Basically, it's a mathematical abstraction where you basically have a set of nodes and a set of edges. And this can be pretty much anything. And on the screen here, you just see a specific regular graph, fully connected graph, which pretty much doesn't mean anything before you give it some meaning. So graphs can be, as I said, anything, and you'll often find like graphs in nature. And so here on the screen, in the top left, you can see one example are molecules. You can naturally model them as graphs, because if you think about it, like the atoms, the individual atoms in these molecules are basically nodes. Then you have bonds, which can be like a single bond, it can be double bond, it can be aromatic bond, and so forth. Then we have like these traffic networks, which can also be modeled as graphs. You have the intersections are nodes. You have the roads, which are connecting those intersections, which are basically edges in the graph. Hopefully that's makes sense. In the bottom left, you can see basically social network, and again, it's very natural to model social networks by graphs, because every single user on this network is basically a node, and then you have connections which are like edges. Finally, you have in the bottom right, you have brain, which is also, you can think of it as a graph, right? You have neurons, you have connections between the neurons. So again, it's pretty natural to model this thing as a graph. So as you can see, anything can be pretty much thought about like a graph, and we'll see some examples a bit later. But that's the first thing I want you to understand if you don't already understand this. So having said that, basically there are, as you can see, 50 shades of graphs. So basically there is a whole like field of mathematics dealing with graphs, and it's called graph theory. And there is so much you can learn before even starting to do GraphML. You can learn so much about graphs themselves. So they are interesting mathematical objects in and of themselves. But for the purpose of this talk, it's more important that you're just aware that they exist out there. So here in the bottom left, you can see a multi-graph where you basically have multiple edges connecting every single node. Then you have directed graphs as the example on the right of the screen, and A points to B. So this is, again, super abstract. Let me give you something more specific. So if you have Twitter, and I assume most of you have, basically, if you follow somebody, like you follow Elon Musk, but Elon Musk doesn't follow you back, obviously, or probably, then that's an example of a directed graph. But on the other hand, if you have Facebook, and if you're a friend with somebody, the friend relationship is bidirectional by default, so you can't be friend with somebody without without that person being a friend of yours at the same time on Facebook. So that's in our example. And then we have concept of self-edges. So that's what I want to tell you there. And basically, I want you to understand that if you start reading research papers in GraphML, there is a lot of simplifying assumptions, and I notice people asking questions like how to apply this to directed graphs, how to apply this here and there. Usually people just take the simplest case and assume that graphs are undirected and that they have self-edges. And we'll be using that same assumption throughout this video, although I won't be getting into any heavy maths, so that's totally fine. So that's all nice, nodes and edges, but in order to actually apply GraphML to any interesting problem, you basically want to add features. And we associate node features, and we associate features, so feature vectors, to both the nodes and the edges of the graph. And that's, again, very abstract. Let me make it a bit less abstract. So there is this famous benchmark data set in GraphML called Cora, and like the semantics of it, it's just a citation network, meaning every single node is a research paper, and the edge in that graph means that paper cited some other paper. So that's the semantics. So what kind of features does Cora have? And the answer would be, so some people just took all of those papers, did some word counting, and basically found the words with the highest frequencies, and then you just sort the words by frequencies. You cut the list somewhere, and they ended up with, like, depending on the threshold was maybe like the lowest number, the lowest count, and you end up with 1,433 words. And so what you do now is the following: if you want to associate a certain feature vector with a certain node, you ask the following question: is this particular word present in this particular paper? And if it is, you just put 1. So for example, kernel may be a popular word, and then you just ask the question, does this paper have kernel as a word inside of it? If it does, you just put 1 there, and you basically get a huge binary vector, and that's Cora. And the expectation is, having that information, you can basically use it to deduce certain or induce a certain information about the graph. In Cora, in particular, you can answer questions like, is this paper published in the reinforcement learning field, etc. Okay, so that's one example. Another example, and I think I mentioned this one already, is molecules. So you can have, like, maybe the edges can be like single bond, double bond, or you can have aromatic bonds, etc. So you can, again, imagine maybe having one hot vector as one trivial example of how you could featureize these edges. Basically, if you have a single bond, you just put maybe number 1 in the 0 slot. If you have double bond, you put 0 in the second slot, etc. So hopefully you already knew this. If you didn't, I'm glad I had this short introduction. And I'll just mention this one slide, and then I'll make a short break. You can ask questions already. So graph neural networks, for now, I'm just assuming this is a black box. For now, I'll later go into a bit more depth. So basically, you have your graph. You can just think of GNNs as basically differentiable computing blobs, and that's all. Like, they somehow process, so you can maybe have some fully connected layers. You somehow transform those graphs. You apply some non-linearities as in other deep learning subfields, and you end up with some certain representations. And then once you have, so that's the outputs part of this chart, and then you can do a bunch of stuff. Again, it's super abstract. You can do graph classification, graph regression. You can do node and edge classification and regression, and that can be anything. And I'll give you specific examples of what those mean in a second. So yeah, that's a pretty much black box for now. And I want to just tell you about some exciting implications. But before I start doing that, do you have any questions so far? The thing is, I don't see anybody, so it's weird. So just feel to ask.
Yeah, it's fine. I'll relay. Actually, we just had not exactly a question, but a comment. So from Naima Sid, who says that everybody talks only about the Cora dataset and how to apply GML to ECG signal datasets, or say that the audio waveforms or tabular datasets and perform node classification. So not really a question there, but
More
I
a
guess
statement.
there's a
Sure.
kind of a lurking question. Is there another data set, I guess?
Sure, there is another data set. People, and that's a really legit question. For many years, people used to just test their algorithms on Cora, on PPI, that's protein-protein interaction data set, CiteSeer, also simple data set. And the thing is, you couldn't differentiate between powerful GNN architectures using those, let's say, simple data sets. And there are initiatives, I think it's called Open Graph Data Benchmark. I may be wrong here, but yeah, people are working on this, and it's GraphML in general is still a young, relatively young compared to other research areas, a young field. So yeah, people are going to I assume, introduce something similar to ImageNet, what ImageNet was to computer vision back in 2012.
Mm-hmm. There's another one on datasets, this one specifically on Cora, and from Zenya, who's asking, what do the edges represent in Cora?
So I think I mentioned, so it's a citation network. So basically, the node is a research paper, and the edge means that research paper cites some other research paper. So it has that other research paper as a reference.
All right. Carlos is asking, is machine learning always piled to an existing graph, or can the network be constructed using GNN techniques? I'm
not sure I understood this question. Could you repeat? Or
yeah, sure. So he's asking whether it's piled is the word he uses. I guess maybe I would say attached or applied to an existing graph, or can the network be constructed using GNN?
Okay. Well, you usually do have graph data, and that's an interesting question because there is not an equivalent of a camera for GraphML. So you don't have a camera where you can like capture images. In that case, here you can't just capture graphs. It's a bit more. People usually collect graphs, and there are some natural applications like social media where you are naturally building up those graphs. But yeah, I'm not sure if I understood your question well. Maybe we can answer it a bit later. Okay, so applications. First application I want to mention is this Uber Eats application. And you can see here, it can be really nicely modeled as a graph. So you have users, which are, again, nodes in this graph. You have food in this example, which are, again, nodes. And it's a multimodal graph because you have different entities here. You have users, profiles, and you have food. Uber, in particular, they had a separate graph for restaurants and users. So if you have a question, why don't they mix everything together? Because it was easier to decouple it like this, I assume. And that was back in a couple of years ago. So maybe they improved it in the meanwhile. But basically, what you do here is, so here we have a particular case where we are doing edge regression. Why edge regression? Well, what they're doing here is you basically want to answer the question, how likely is a user to order a certain food item? So basically, let's take the hamburger, and if the edge has a value of 1, that means this user is 100% sure to take hamburger. If the pizza is maybe 50% or 0.5, so the user has 50% to order it. And then you can just imagine how you can just sort the edges according to those probabilities, according to those numbers, and you can kind of recommend the food items to that particular user. So that's an example of how you could do edge regression. Okay. Second example is this very famous example in GraphML. It's called PinSage. And basically, what it did here is there is this platform, you're probably familiar with it or heard of it, Pinterest, where you collect these pins. They are visual, they are textual. You're basically collecting some interesting pins in boards, etc. And what it did is they leverage graph neural network called PinSage to create much better recommendation engine, and that's a big deal. Like out of all of AI applications today deployed currently in the world, like we're talking about self-driving cars, etc. But basically, in my opinion, and I think many people share that opinion, like recommendation engines are influencing our lives big time. And the very fact that graph neural networks are already deployed there is very exciting. And as you can see here, like this image of people lodging this tree, And if you take a look, like if you just use the visual baseline where you find content, where you recommend content based on how visually similar it is, you can see there are semantic errors. So you can see like soldiers running, and that doesn't have anything to do with this input image. It's just that it's grayscale, so it's similar in appearance, but totally they like kind of missed it. Then we have annotations, which are a bit better, but you can see the trees, but it's not grayscale, so it's not that similar visually. And finally, so Pixie is some stronger baseline they had. And finally, they have PinSage, which combines both the visual information with the textual information, and basically combines it with the structural information in the graph in order to give much better recommendations. Okay, and the third example here is a Twitter network. Basically, what they did here is node regression, whereby they associate a certain probability that a user in this Twitter network is likely to spread fake news. So the red ones are users which are prone to spreading fake news. The blue ones don't spread fake news. And the interesting fact about fake news is that the propagation pattern is really interesting, and it can be detected by looking how it evolves over time. And using that, they deployed a graph neural network here to kind of solve, let's say solve, not solve, but to tackle this task. That's another exciting application, and all of these graphs are huge, like social networks like Uber, like Pinterest, and finally Twitter. Now, let me show you some more like fundamental ones. So going into science, and this one you probably haven't heard unless you've been following me on LinkedIn or somewhere. Basically, this is IceCube, and that's a huge laboratory in Antarctica, and you can see like the Eiffel Tower in the bottom left, and you can see the city on the right picture, which just represents how huge this thing is. And what they do is they basically have a grid-like structure of light sensors, and what happens is they're trying to capture neutrinos, so high-energy particles coming from some high-energy events like supernova explosions. And what happens is that neutrino comes in, it interacts with the molecules of the ice, because this thing is kind of digged into ice. And what happens is that while the neutrino is going through the ice, it interacts with molecules, and there is this effect called triangle of light, which gets emitted, and then this light sensors can kind of capture it, and then you can see these red blobs. The size of the blob kind of depicts how much light, how much energy has that sensor received. So the bigger the blob, the more energy. And again, you can see that the graph pattern forms here. Again, deploying GNN here, they got really nice results on the classification task, much better than previous classical techniques they used. There is one more example with cancer. That's all interesting. I'll have to speed up. I don't think I'll have time to tell you about everything, but this one is really interesting because they're doing a multi-relational regression. So basically you have proteins, you have drugs. So the triangles are drugs, the proteins are yellow circles. And applying a graph neural network, you can answer the question whether two drugs, so take C and triangle S, you can ask the question whether a certain side effect is present or not present. Again, you have a number between 0 and 1. The neural network can regress those numbers, and you can answer a really important question, and that's whether there is a side effect if you combine two drugs. And that's called a polypharmacy side effect, and many people are kind of impacted by this fact, especially our grandparents. And so you can imagine it's really important to solve this automatically, because as you can imagine, it's really hard to manually screen all of the possible, the combinatorial space is too huge. We need computational methods to solve this kind of tasks. So those are some interesting. Yeah, one more. This is super famous. Again, they had a data set of molecules which inhibit Escherichia coli, and by training it on that data set and then deploying it on some unknown molecules, they were able to sort out some molecules which showed high potency against Escherichia coli, and previously unknown molecule called, now dubbed helicin, as you can see on the picture, was discovered, and it was previously just like they just used it in the context of diabetes. So this was a novel application. Nobody thought of it, and it's really potent. So you can just imagine how this can be a really valuable tool in a toolkit of every single chemist, and biologist, etc. So hopefully I hyped you enough. Now what I wanted to do is kind of contrast GraphML. So that was all nice, but I wanted to kind of make a link between GraphML, computer vision, NLP, and RL. So first of all, if you think about it, images are basically graphs. And you can see here on the screen like a simple regular graph, also called grid. And if you kind of assign values to every single node, you basically have a grayscale image. Or if you assign vectors, you have like three numbers like RGB. You can have like a fully colored image. Again, videos are just 3D grids. So yeah, but just the pure fact that it's a graph doesn't mean you should use, I'm not saying you should use GNNs just because it's a graph. And the reason is like neural networks such as convolutional neural networks have a really good biases ingrained into them. So you should use them if they are giving better results. But people are already starting to explore using GNNs on images in computer vision in general. Yeah, just keep that in mind. The second thing is, if you think about it, transformers are a special case of graph attention network, and this may be hard to understand initially, but if you treat a sentence as a fully connected graph, so if you connect implicitly every word with every other single word, basically what transformer does is the same thing as what graph attention network does. And I implemented both from scratch, so I do understand this a bit better. I do appreciate that if you're novel to this field, this will be confusing, but just keep that connection somewhere in mind. Like basically, graph attention network is a generalization of transformers, and it can be applied to any other type of graph, not just fully connected graph. And finally, reinforcement learning. Now, this may be strange for some of you why I'm mentioning RL here. Basically, the reason is, so basically RL can leverage any one of these advancements. It can leverage advancements in computer vision. It can leverage advancements in NLP. The reason I'm mentioning it because basically the scope of applications for RL currently is pretty narrow. And I've been doing lots of RL over the last period and implementing DQN, but they are only applicable to pretty much to games because there is a lot of data, and to robotics. So compare that and CV as well and NLP with GraphML, and you can see how homogeneous they actually are compared to GraphML, because you already saw some of the applications, and that's not the whole list. Okay. If you have any questions, I'll stop here again.
I'll jump right in here. So actually, there's a few questions from the previous break that we didn't have time to cover, so
I'm listening.
Pass them on. So Nikhil is asking, are GNNs being implemented in spiking neural networks?
What was the question? Are GNNs being implemented in spiking neural networks?
Mm-hmm.
I'm not sure I understand that. I can assume you're maybe asking whether there is a connection, whether people are using neuroscience as inspiration and integrating some of those ideas into GNNs. If that was the question, I haven't seen any paper that deals with that. Having said that, that doesn't mean it doesn't exist. I'm not aware of anybody using those spiking mechanisms and ingraining them into GNNs, if that was a question.
I'm not sure either, but I hope that answers it. There's a couple of people asking for a reference for the Twitter fake news example, but I guess you can give that one offline, probably.
Sure. By the way, I wrote a blog. I made a lot of videos. Have a project. So I'll share some of those. Like some of the best people in the GraphML field told that that's a good way to start. So I do believe them.
Mm-hmm. Okay, that's cool. And then I guess you also have a final part of the presentation, so I'll just keep past one last question for now, because we have in total 7 minutes left, I think.
Okay.
So In the training process, how would you take a sub-sample of the graph for training and test sets? And how would that change for the Cora dataset or the protein interaction graphs? And then again for node, edge, and graph classification.
Well, in Cora, the thing is you have two modes of training when you train GNNs. You can have transductive approach, you can have inductive approach. Transductive approach means you have a single graph, and the thing is some of the nodes have labels, most of them do not have labels. And then what you're doing there is you're training the GNNs on those labeled nodes, and then once the training is done, you can ask questions like some of the other nodes which doesn't have label, you can ask which label does it have, and that's the transductive approach. The inductive approach, and basically you're given those labels. You can't. It's not like you decide. It's like you only have labels for those nodes and you don't have the labels for the other nodes. So that's the transductive approach. The inductive approach, like PPI, again, basically somebody made a split between the training and testing data sets. You train on the training graphs. So you have multiple graphs there, not a single one as in the transductive case, and then you kind of do inference on the test set. Pretty much the similar like pipeline as in any other subfield of machine learning.
Okay.
Short overview of the field, as much as I can do in 7 minutes. So basically, everything started with this graph embedding methods. And if you're familiar with natural language processing, NLP, you know about word-to-vec method. The main idea there was you do the following. You basically sample sentences, and you have some table of vectors, which are your embedding vectors. And what you do is the following. So if the words tend to appear close together, you want to make sure that their vectors are really similar. So you achieve that by just doing a dot product, and you want to maximize that dot product. If they appear together, the vectors should be similar. If they don't appear together, the vectors shouldn't be similar. As easy as that. And what happens is that this beautiful thing emerges, and that's the structure in the latent space, in that embedding vector space. And you can see here the example where you have man, like that's one embedding vector. You just kind of down project it. You do some dimensionality reduction method so that we can visualize it in 3D. And now we can see the man vector, we can see the woman vector. And in parallel, you can see the blue dot, and for some reason you can't see it, but yeah, it should be king. And you can see queen down there. And you can see that the analogies, they're almost parallel to each other. And that's an awesome property that many other subfields later try to exploit. And you can see here an example of my implementation of this again, where you can do a similar thing. You have like the embedding vectors of happy women. Once you decode that, you get these images. It's low quality because it's an older method, but you average those vectors and you get on the right, you can see happy woman average. Then you have neutral woman average, you have neutral man average. And what you do is the following. You subtract the neutral woman vector from the happy woman vector, and you get a notion of happiness, like a vector that encodes happiness. And then you just add that vector to the neutral man, and you end up with the happy man face down on the bottom. And that's pretty exciting. Similar thing happens in GraphML. So people were inspired by this paper by Mikolov in 2013, the word-to-vec, and they started doing the same things in GraphML, so methods like deepwalk and node2vec, and you can basically treat this as the following. So you have a graph, and if you do random walks across that graph, and if you treat the nodes as words, you're basically doing the exact same thing as word-to-vec. You're basically sampling sentences, and which are nodes in this example, and you want to make sure that the nodes which appear together in those random walks have similar embeddings. Once you train the embedding method like that, you can see on the right, and again, you just project it into 2D. You can see there is some nice properties. Similarly labeled nodes appear clustered together in the 2D space. Okay, I won't have enough time. I just want to motivate some of the GNNs here. So first of all, you know about ImageNet and that convolutional neural networks did miracles for CV community. So we somehow want to generalize the notion of convolution to GraphML. So that's the first trick that the researchers had to solve. And The second thing is just background. So here you can see degree matrix. Basically, you take one node, like maybe node 1. But so you have this node 1, and you can see it's connected to node 2 and node 5. If you take a look at the degree matrix, you can see that the first row has number 2 there, because that's the degree of that node. Then we have adjacency, so that's the degree matrix. Hopefully that makes sense. So if you take a look at the node 6, it only has one edge, and hence in the last row number 6, you have only one. The adjacency matrix kind of just represents the connectivity of this graph. Once you subtract the adjacency matrix from the degree matrix, you get something called Laplacian matrix. And that's the main object, mathematical object, that's being used in these first GNNs, which I'll explain on the next slide. The second important concept is a signal on the graph. And what a signal on the graph is the following. So basically, to every single node, you just associate a certain number or a certain vector, and you can visualize those via these vertical lines. You can see if the number is high, there is this large red line. If the number is low, below 0, you have these vertical lines that go below. So there's just a visualization of what a signal on the graph is. And having that theory checked, let me now just tell you about spectral methods quickly. They rigorously transfer the mathematical notion of convolution to GraphML. The bad things are that it's super expensive to use them. They are inherently transductive, so that means because they're basically using a specific Laplacian matrix, and that Laplacian matrix corresponds to one and only one graph. That means once you train a GNN on this graph, you can't apply to some other graph that has some other structure. So that's the bad thing with these methods. There are some other things, but I won't get into those details. Just let me tell you about some other important things like spatial GNNs. And these are the name of the game. They are scalable. They are the ones being deployed currently in all of those exciting applications. And you have, the first one is the GCN. That's the one you can see here. So the graph convolutional network, the first truly scalable network, loosely inspired by spectral method, but basically it's better to treat it as a spatial method. And then you have a graph attention network here. You have GraphSage, which did a further step which improved the scalability by just subsampling a set of nodes and only doing these aggregations on top of those nodes. Yeah. Maybe a quick explanation here. The thing you do with spatial GNNs, so how it works is really easy to explain conceptually. You have a certain node, and you just take a look at the neighbors of that node, and all of them have feature vectors, right? What you do is you somehow combine them, maybe some mean average, maybe you weigh them by the attention coefficients. You combine them, you pass them through a nonlinearity, and you get the feature vector on the next level of the graph neural network. And that's how they do. You basically have a bunch of nodes, you process them by looking at their neighbors, and you do that aggregation, you do that nonlinearity, and you are on the second level. And GNNs are usually shallow, so you'll see 2 to 3 layers top, compared to CNNs, which are usually deep, and that's a separate topic in and of itself. I can link some really cool blogs, and you can check that out for yourself. Okay.
I'll have to jump in here, and hope you are happy with having that wrap up your talk, because we have to close, unfortunately. Thanks, Aleksa.
Thank you.